Welcome to Lecture 31 on regularization. Today we are going to look at methods to solve the problem of overfitting. So there are three sections of this lecture. We first want to talk about the motivation of regularization from the angle of VC analysis. And then I want to give you some examples of how do we do regularization. Then I'm going to introduce two techniques of regularization. One is called the weight decay method. The other one is called the augmented error. Both methods we have actually seen them during the first few lectures of our entire course. And so these regularization functions, you can treat them as putting a 2-norm square, putting 1 norm on the objective function. Or you can put them into a constraint. So we will visit these during the second part of our lecture today. The third one is how do we choose the regularization? What will happen if we choose a bad regularization? And what will be the role of the regularization parameter lambda? So the starting point of this lecture is the problem of overfitting. Let's imagine that you have 5 data points and you have a target function given by a blue curve. So in this picture, you can see that I have 5 data points that are drawn from the blue curve. And when I try to solve the learning problem, I will cover the blue curve and I will only see the 5 data points. Then I will try to fit the data points using a curve. And let's say I'm choosing a 4th order polynomial in this case, and I try to fit all these 5 data points. And you can see that because I only have 5 data points, I'm using a 4th order polynomial. Then since I have enough degrees of freedom, I will give you a perfect fit of the data points. This is a free fit situation where you do not constrain anything about your model. Here is a restricted fit, which I'm still using a 4th order polynomial. However, I put a regularization term over there. I say that the magnitude of the 4th order polynomial, the coefficients, they cannot be too big. So I'm putting a constraint over here, and then suddenly you can see that my fitting becomes much, much better. So this is the power of regularization. We want to understand how regularization is going to help us in solving the overfitting problem. So regularization is one weapon to combat overfitting and constrain the learning algorithm to improve outsample error when there is noise. And regularization is as much as an art than as it is a science. Now, why do I say that? Well, because regularization is a set of heuristic tools which has been tested to be very, very useful. Now, as for how to choose the right regularization function, in fact, there is no clear answer of how do we choose the regularization function. Why do we want to choose a 2 norm? Why do we choose a 1 norm? There's really no clear definition unless you really know how the data are being generated. So let's look at the regularization from the perspective of a VC analysis. And by doing this, we will try to understand how regularization are being formulated and why will regularization help us to solve the testing problem. Now, from your mind, you may be thinking that regularization is just to put a term, like a penalty term, in addition to the data term that I usually see in an optimization problem. But by putting a regularization term, why would it help us to solve the generalization? Meaning that why putting a regularization function into the minimization problem can help me get better testing error? Now that is not very clear from a pure optimization point of view, because optimization would just say that give me a penalty term and then I will be able to do some kind of regularizing your solution. But why would this minimize your outsample error? Why would this minimize your testing sample error? That has to be analyzed using the VC technique. So when you look at the VC analysis, you realize that suppose I have one hypothesis H and that is drawn from my hypothesis set H. Then I calculate the testing error E out, and I compare with the in-sample error with the training error E in. Then we realize that there's always a term omega of H. Okay, so this omega, if you recall, that is the confidence level of your estimate, and that will be a function of your hypothesis set That will be a function of the number of training samples. That will also be the function of your confidence level. So this is an omega function here, and it is always there in the upper bound of your VC analysis. So this omega h, you can also call it the model complexity. And if you want to minimize your E out, okay, so this is your testing error. If you want to minimize this guy, one possibility is to minimize the upper bound. If you can make the upper bound as small as possible, then in principle, your outsample error should also be minimized. So roughly speaking, what you can do is that in this number, this is the omega on the entire hypothesis set H. What you can do is that you can choose a simple H coming out from the hypothesis set H. So in other words, what you can do is that you can effectively minimize this function, which is to minimize the in-sample error, plus some kind of measure on H. Now here the omega can be something which I haven't really defined it yet. But imagine that omega is something that can measure the complexity of my small h. Then by minimizing this, I should, in principle, minimize the upper bound, and hopefully that can help me minimize my outsample error. Now this is very heuristic. There is no math behind this. This is just saying that, look, this is the generalization bound. And because I want to have a constraint on my hypothesis set, I want it to be as simple as possible. Then I want to do something over here to minimize a measure of the complexity of a choice of the hypothesis. If I can minimize that, I will hope that that can minimize my outsample error. So that is, instead of minimizing just the in-sample error, I want to minimize this omega h2. Now, although this is very heuristic, that at least gives you some kind of tool to help you understand that why, by minimizing the sum of the in-sample error and also the complexity of the hypothesis, we have a hope to minimize your outsample error. This is not very clear from the optimization point of view, because if you just look at optimization, that will just tell you that because your solution is underdetermined or overdetermined, that problem is not very good, and so you want to stabilize the solution. You do not have that perspective of getting a better estimate from the generalization point of view. But if you look in this way, then you can see that the VC analysis tells you that by minimizing this function, you can indeed minimize the upper bound, roughly speaking, and therefore you can roughly speaking minimize the testing error. So let me give you an example of how can we do that. This technique is called weight decay method, which we will visit again in the second part of this lecture. The idea is very simple. It says that I'm going to measure the complexity of my hypothesis using the number of coefficients that are used to represent my model. So in other words, I would prefer to have mild lines with small offsets and slopes. So let's say you have a linear equation, and then you have a line. So that will be described as W transpose X. So that would be your linear equation. You may want to say that the magnitude of all these coefficients has to be as small as possible. Or you can say that the number of coefficients to be as few as possible. So there are different ways of controlling the coefficients in a linear model. So if you apply this concept to the sine example that we have shown you previously, let's say you have a sine curve, and then you only have 2 data points, and then you can use a 0th order polynomial, a 1st order polynomial, and so on, and you try to fit that. If you recall the curve that we have shown you before, this is the free fitting situation where you just give me 2 data points, 2 data points, and then you try to fit the 2 data points, and you can see that it is everywhere. However, in this case, where you try to constrain the magnitude of your slope and also the y-intercept, then you can certainly reduce the variation of all these curves. And therefore, you can see that this weight decay method, by just limiting the magnitude of your coefficients in this linear model only have two parameters. It will be the slope and also the y-intercept. By controlling the magnitude of these two parameters, you can have a much better fitting to the curve using just two data points. Okay, so let's recall what we had before. If you use a constant model, you have the EL being 0.75. If you use a regularized model using the first order polynomial, you get 1.9. But then if you use a regularized model for the first order polynomial, you can actually go below the constant model. Okay? And so if you want to look at it from the bias variance point of view, what you are trying to gain is that you are gaining the variance. You make the variance a lot lower. However, you have suffer from the bias. Now, why do you have a suffer from the bias? Because you say that my coefficient, my slope and my y-intercept, my magnitude of the coefficients has to be controlled, and therefore you're restricting yourself to a different set of solutions, and that will create a bias. Now the variance is reduced because then you can control the magnitude, and so the fluctuation of your estimate will be reduced. Now the hope is that in this bias variance analysis, the variance drop is more than the bias gain, and therefore the overall testing error will be reduced. So here is a curve showing you what will happen if you only use two data points. Without regularization, you have a bias of 0.21. And then you have a variance of 1.69. This is a very, very large number of variance. If you use the regularization that I introduced before, which is that you control the magnitude of the coefficients. Now, I haven't talked about how we actually do that. I'm just saying that there should be a way to control the magnitude of the coefficients. Then if you do that, then you can see that the bias becomes 0.23 versus the variance goes to 0.33. And so there is a gain in terms of the bias, but the drop in the variance is more significant, so that when you add the two up, your overall testing error is reduced. So why do we need regularization? This example should be clear that the linear model that we're considering is just too sophisticated for the two data points that I have in this example. Now, of course, if you have 10,000 samples, 10,000 training samples in this problem, then the linear model may not be that problematic. Because then as you recall, if you have a lot of data points, then eventually you will just try to fit the sine function using a straight line, and that will be very, very good. Now, because we do not have enough data points, then the linear model, the first order model, is just too sophisticated. And in other words, any 2 points can be fitted by a line. And this problem is still there even if we change the target function, not just a sine function, maybe cosine function, you change an arbitrary hyperbolic function, you will still have the same issue. And so the regularization really depends on how many data points you have and what is the quality of the data points. If you only have a few data points, then you better want to use the regularization. If you have a lot of data points, but the data points they are very noisy, you may also want to consider using regularization. So given only 2 data points, what you can do is you can either choose to use a simpler model, let's say, for example, the constant model, or you can constrain the model using the weight decay function that we're going to study in more details later on. So constraining the model gives us more flexibility because you can control, not just saying that I want to fix a particular model using a lower order polynomial, but you can say that I want to control the magnitude in certain ways that can give you freedom.